Welcome back to Sleeping with Facts. Tonight, we are turning off every light except the quiet glow of the stars themselves, and settling in for a slow journey through the life of a star, from the first drifting clouds of dust to the dense, silent remnants left behind. There is nowhere to be and nothing to do but listen, so let your body sink into the mattress, let your breathing slow, and let the universe carry you gently towards sleep. There will be no jump scares here, no rush, no urgency, only the patient, unhurried unfolding of the cosmos, the way it has unfolded for billions of years before you and will continue long after. Somewhere above you tonight, in the quiet dark beyond the ceiling of your room, beyond the atmosphere, beyond the reach of anything you could touch, there is a cloud. It is not a cloud like the ones that drift over your house in the daytime. It is made of hydrogen and dust, spread so thin that if you gathered a cubic centimeter of it in your hand, you might find only a single atom resting there. And yet, across many trillions of kilometers, that thin, quiet material is enough. It is enough to eventually become a star. It is enough, one day, to become a sun that warms a small blue planet, or perhaps, one day far in the future, a small quiet room where someone is falling asleep to the sound of a voice describing exactly this. Tonight, we are going to follow that thin cloud on its long, slow journey. We will watch it fold in on itself over the span of what would feel, to us, like an impossibly long stretch of time, hundreds of thousands of years, folding, gathering, warming almost imperceptibly, degree by degree, as gravity does its patient work. There is no rush in this process. There has never been any rush in this process. The universe does not hurry, and for the next several minutes, neither will we. We will watch a star settle into what astronomers call its main sequence, that long, stable middle chapter of its life, where hydrogen fuses quietly into helium at its core, releasing a soft and steady light that can last for billions of years. We will consider how our own sun sits in the middle of that chapter right now, roughly 4.5 billion years into an expected lifespan of about 10 billion, shining with the same patient rhythm it has held since before there was an Earth to receive its light. And then, later in this documentary, we will move gently through what happens as that light begins to change. How a star swells, cools at its surface into shades of amber and deep red, and slowly reshapes itself into something new. We will talk about how the outer layers of a star can drift outward into space, spreading into wide, soft shells of gas that catch the light of what remains behind, forming the shapes we call planetary nebulae. Some shaped like rings, some like hourglasses, some like the wings of something that might, if you squint, resemble a butterfly resting quietly in the dark. For the largest stars, the ones many times more massive than our Sun, we will talk about a different, more dramatic transformation. One where the core becomes so dense and so tightly packed that its protons and electrons merge into neutrons, forming an object barely 20 kilometers across yet holding more mass than our entire Sun. This is the neutron star, one of the densest objects known to exist, a single teaspoon of its material outweighing a mountain here on Earth. We will describe this not as a catastrophe, but as a transformation, a settling into a new and stable form, one that can then spin quietly for millions or even billions of years, sweeping steady beams of radiation across the galaxy like a slow, distant lighthouse. None of what we describe tonight needs to be alarming. Stars have been living and changing in this unhurried way for over 13 billion years, and the processes that shape them are, in their own way, remarkably calm, vast stretches of stillness, punctuated by slow, gradual change. Even the most dramatic moments in a star's life unfold according to physics that has been quietly understood, measured, and mapped by patient scientists working with telescopes pointed steadily at the sky for generations. As you listen tonight, you do not need to remember any of the details. You do not need to hold onto the numbers, the names of the nebulae, the exact distances in light years. All you need to do is let the shape of the story wash over you. Clouds gathering into stars, stars shining steadily for eons, stars slowly changing as they age, and finally, stars settling into quiet, dense remnants that continue to exist long after the light show has ended. Let your eyes grow heavy. Let your shoulders soften into the bed beneath you. Let the pace of this description become the pace of your own breathing, slow and even and unhurried. Around us, right now, the material that makes up your body, the calcium in your bones, the iron in your blood, the oxygen you are breathing in and out as you listen, was formed inside stars very much like the ones we are about to describe, long before our solar system existed. You are, in a very real and gentle sense, made of old starlight, old stellar material, patiently recycled across billions of years into the shape that is reading, or listening, or simply resting right now. There is something quietly comforting in that thought, something worth carrying with you into sleep. So let this be your invitation to rest. We are going to spend the next several hours moving slowly through 11 chapters, each one describing 10 gentle facts about the stars, from the nebulae where they are born, to the long stability of their main sequence years, to the graceful and sometimes striking transformations that occur near the end of their lives, and finally to the dense, quiet neutron stars and other remnants they leave behind. There is no need to stay awake for all of it. In fact, it is our hope that you will not. Let your mind wander gently along with the description, and if you drift off partway through, know that the universe will still be here, unfolding at its own slow pace when you wake. Let us begin, softly, with the clouds. Nebulae are vast clouds of gas and dust that drift quietly through galaxies, composed primarily of hydrogen with smaller amounts of helium and trace heavier elements woven through them. These clouds can span distances of many light years, their edges fading softly into the surrounding darkness of space rather than ending in any sharp line. Within their folds, gravity works slowly across thousands of years, gathering matter into denser pockets that will one day become something new. The Orion Nebula, one of the closest stellar nurseries to Earth, lies roughly 1,344 light-years away and remains visible to the naked eye on a clear, dark night. Its soft glow comes from hydrogen gas being gently warmed and excited by the light of young stars nearby. The word nebula comes from the Latin term for mist or cloud, a name chosen by early astronomers who observed these hazy patches through comparatively modest telescopes centuries ago. Before the 20th century, many nebulae were mistaken for distant clusters of unresolved stars, or in some cases even mistaken for entire separate galaxies. It was only with improved instruments and longer exposure photography that astronomers began to reliably distinguish true gas clouds from these other cosmic structures. Today, catalogs such as the New General Catalog list thousands of these formations spread across the observable sky. Each entry quietly represents an ongoing process of stellar formation that continues largely unseen by the unaided human eye. Emission nebulae glow with their own light, produced when ultraviolet radiation from nearby hot young stars ionizes the surrounding hydrogen gas, causing it to emit a soft, reddish glow across great distances. Reflection nebulae, in contrast, do not produce their own light but instead scatter the light of nearby stars, often taking on a gentle blue hue caused by the way fine dust particles scatter shorter wavelengths of light. Dark nebulae contain dense concentrations of dust that quietly block light from objects behind them, appearing as soft silhouettes against brighter backgrounds of stars. The Horsehead Nebula is a well-known example of this dark, silhouetted form, resting gently within a brighter field of glowing gas. Each type reveals a slightly different characteristic of the same underlying material drifting slowly through space. Molecular clouds, the coldest and densest regions found within larger nebulae, can reach temperatures as low as 10 to 20 degrees above absolute zero, a stillness colder than almost anywhere on Earth. It is within these cold, quiet regions that the earliest stages of star formation typically begin, as gravity slowly draws gas and dust together over immense spans of time. These clouds are largely composed of molecular hydrogen, along with trace amounts of carbon monoxide, which astronomers use gently as a tracer to map their hidden structure. The Taurus molecular cloud, located about 430 light-years from Earth, is one of the nearest and most studied regions of this kind. Its wispy, filament-like structures have been mapped in fine detail using radio telescopes over many years of patient observation. Planetary nebulae, despite their name, have no true connection to planets and instead form when a sun-like star gently sheds its outer layers into space near the end of its evolutionary path. The remaining hot core illuminates the expelled gas from within, producing intricate and often symmetrical shapes that can resemble rings, hourglasses, or the soft outline of butterfly wings. The Ring Nebula, located in the constellation Lyra, is one of the most photographed examples of this quiet, expanding structure. These formations typically last for only about 10 to 20,000 years before dispersing gently into the surrounding interstellar medium. The name itself arose because early astronomers, viewing them through small telescopes, thought their round shapes resembled the soft disks of distant planets. Supernova remnants form a separate and distinct category of nebula, created from the outer material gently released by a massive star at the end of its long evolutionary path. The Crab Nebula, located about 6,500 light-years away, is the remnant of a stellar event recorded quietly by astronomers in the year 1054. Its filaments continue to expand outward at speeds of over 1,500 kilometers per second, gradually cooling and thinning as they spread across space. At its center rests a neutron star, spinning rapidly and emitting regular, steady pulses of radiation outward. This remnant offers researchers a detailed and patient record of how stellar material disperses and slowly mixes with the surrounding gas over centuries. The interstellar medium, the thin material filling the space between stars, is not truly empty but instead contains gas, dust, and cosmic rays distributed unevenly across a galaxy's vast expanse. Nebulae represent the denser regions within this medium, where matter has slowly begun to concentrate under the gentle, patient pull of gravity. On average, the interstellar medium contains roughly 1 atom per cubic centimeter, an extraordinarily sparse density compared to the air we quietly breathe on Earth. Despite this thinness, the sheer volume of space means that nebulae can still contain enough material to eventually form thousands of new stars. This slow accumulation over millions of years quietly illustrates how structure gradually emerges from what once seemed like near emptiness. Some nebulae, known as HII regions, are named for the ionized hydrogen that fills them, a state in which hydrogen atoms have gently lost their electrons due to intense ultraviolet radiation from nearby young stars. These regions often mark the presence of newly formed, massive stars still resting embedded within their birth clouds. The Eagle Nebula, home to the well-known formation called the Pillars of Creation, is a striking example of this active stellar nursery. Structures within it stretch across several light-years, with dense columns of gas and dust shaped slowly over time by radiation and gentle stellar winds. These pillars are believed to be gradually eroding, thinning slowly as the surrounding young stars continue to shine steadily nearby. Dust grains within nebulae, though comprising only about 1% of the total mass, play a quietly important role in the chemistry and physics of star formation. These grains are typically composed of silicates, carbon compounds, and ice, and they help cool the surrounding gas by gently radiating away thermal energy. This cooling process allows gravity to overcome internal pressure more easily, encouraging the gradual, patient collapse needed for star formation to begin. Dust also provides quiet surfaces upon which simple molecules can slowly form, contributing to the chemical complexity found throughout these regions. Infrared telescopes are particularly useful for studying these dusty regions, as they can gently detect the warm glow released by heated dust particles. Nebulae are not static formations. They slowly change shape and composition over spans of thousands to millions of years, shaped gently by internal gravity, radiation pressure, and the winds released by young or aging stars nearby. Some nebulae will eventually collapse further to form new stellar systems, while others will disperse gradually into the broader interstellar medium surrounding them. Observations from telescopes such as Hubble and, more recently, the James Webb Space Telescope have allowed astronomers to study these gradual transformations with far greater clarity than before. Comparing images taken years apart reveals subtle, quiet shifts in the structure of nearby nebulae over time. This ongoing, unhurried transformation reflects the broader, patient rhythm found throughout the entire life cycle of stars. A protostar begins its existence as a dense knot within a molecular cloud, a small region where gravity has quietly overcome the outward pressure of the surrounding gas. Over tens of thousands of years, this knot slowly contracts, drawing in more material from its surroundings and gradually increasing in both density and temperature. As the material falls inward, it releases gravitational energy in the gentle form of heat, warming the forming core degree by degree. This process is far too slow to observe directly within a human lifetime, unfolding instead across timescales that stretch far beyond ordinary experience. Astronomers instead study many protostars at different stages, piecing together this quiet story from a wide gallery of snapshots. As a protostar continues to gather mass, it becomes surrounded by a flattened, rotating disk of gas and dust, a structure astronomers refer to as a protoplanetary or accretion disk. This disk forms naturally as the collapsing cloud's rotation causes material to spread outward into a relatively thin, spinning shape rather than falling in a perfectly straight line. Material from this disk continues to slowly spiral inward, feeding the growing protostar at its center over hundreds of thousands of years. It is within these same disks, later in the process, that planets may eventually and gradually form. The disk itself can extend for hundreds of astronomical units, a gentle spinning ring of raw material surrounding the young stellar core. During this early stage, many young stellar objects produce narrow jets of material that stream outward from their poles, a phenomenon known as a bipolar outflow. These jets travel at considerable speeds, sometimes exceeding several hundred kilometers per second, yet they emerge gently and gradually rather than suddenly. When these outflows collide softly with surrounding gas, they can create glowing knots known as Herbig-Haro objects, first catalogued in the mid-20th century. These structures provide astronomers with visible evidence of the otherwise hidden process happening within the dense, dusty cloud. Over time, these outflows help the young star shed excess angular momentum, allowing it to continue settling calmly into its next stage of life. The core temperature of a protostar continues to rise gradually as gravitational contraction proceeds, eventually reaching several million degrees at its center. It is at this threshold that hydrogen nuclei begin to fuse together into helium, a process known as nuclear fusion, releasing energy that will sustain the star for the majority of its life. This moment marks the quiet transition from protostar to a true star, though the process itself unfolds gradually rather than as a single distinct event. The onset of steady fusion establishes an internal balance, known as hydrostatic equilibrium, between the outward pressure of released energy and the inward pull of gravity. This balance, once achieved, can remain remarkably stable for billions of years. Not every collapsing cloud of gas grows massive enough to sustain steady nuclear fusion at its core, and objects that fall short of this threshold are known as brown dwarfs. These objects occupy a quiet middle ground between the largest planets and the smallest true stars, generally possessing between roughly 13 and 80 times the mass of Jupiter. Because they cannot sustain hydrogen fusion in the way true stars do, brown dwarfs slowly cool and dim over billions of years rather than shining steadily. The first confirmed brown dwarf, named TEED-1, was identified in 1995 within the Pleiades star cluster. Their faint glow makes them difficult to detect, and many remain quietly hidden within the gentle darkness of surrounding nebulae. Star formation rarely occurs in isolation, and most stars are born together in groups known as stellar nurseries or embedded clusters, sharing the same parent molecular cloud. Within these clusters, dozens to thousands of stars may form gradually over a similar span of time, though not always at precisely the same rate. The Orion Nebula cluster, for example, contains several thousand young stars, many of which remain wrapped gently within the surrounding gas and dust. Over millions of years, gravitational interactions and the gentle dispersal of surrounding gas will slowly cause many of these clusters to drift apart. Our own Sun is thought to have formed within such a cluster, its stellar siblings now scattered quietly across the galaxy. The process of protostellar formation is often accompanied by variability in brightness, as material falling unevenly onto the young star can cause its light output to fluctuate gently over weeks or months. Stars in this phase are sometimes classified as T Tauri stars, named after a prototype star discovered in the constellation Taurus. These young objects typically range in age from under 1 million to about 10 million years, a relatively brief window in the overall lifespan of a star. Their surfaces are often marked by magnetic activity, producing gentle star spots and slow, irregular changes in luminosity. Studying these fluctuations helps astronomers understand the slow settling process a star undergoes before reaching long-term stability. The overall time required for a star like our Sun to form, from the initial collapse of a molecular cloud fragment to reaching stable hydrogen fusion, is estimated at approximately 50 million years. This span, though brief on a cosmic timescale, represents an enormous stretch of time by any human measure, roughly 10,000 times longer than the whole of recorded human history. Larger, more massive stars form considerably faster, sometimes reaching stability within only a few 100,000 years due to their stronger gravitational pull. Smaller stars, in contrast, may take even longer than the Sun to settle into their stable phase. This wide range in formation timescales reflects the quiet diversity found among stars of different masses. Radio and infrared telescopes play a particularly important role in studying protostars, since these young objects remain hidden within thick layers of dust that block visible light almost entirely. Instruments such as the Atacama Large Millimeter Array, located in the high desert of northern Chile, allow astronomers to peer gently through this dust and observe the faint heat signatures of forming stars. These observations have revealed intricate spiral structures within some protoplanetary disks, hinting at the slow gravitational processes shaping future planetary systems. The quiet glow detected by these instruments represents heat radiating gently from material that will, in time, become part of a stable star. This patient, indirect method of observation has reshaped much of what is understood about early stellar life. Once a protostar completes its gradual transition into a stable, hydrogen-fusing star, it settles onto what astronomers call the main sequence, a long and remarkably steady chapter that can last for billions of years depending on the star's mass. This transition marks the quiet conclusion of the formation process and the beginning of a much longer period of gentle, consistent shining. The exact position a star occupies on the main sequence, and how long it will remain there, depends primarily on its initial mass, a relationship first clearly described in the early 20th century through the work of astronomers Ejnar Hertzsprung and Henry Norris Russell. Their diagram, now known as the Hertzsprung-Russell diagram, remains a foundational tool for understanding stellar evolution. From this point forward, the star settles into the long, calm middle years of its life. The main sequence represents the longest and most stable chapter in a star's life, a period during which it quietly fuses hydrogen into helium within its core at a steady, unhurried rate. During this time, a delicate balance is maintained between the inward pull of gravity and the outward pressure created by the energy released through fusion. This equilibrium allows a star to shine with remarkable consistency for an extended stretch of time, sometimes lasting many billions of years. Our Sun has remained on the main sequence for approximately 4.6 billion years and is expected to continue in this stable state for roughly another 5 billion years. This long, calm middle age forms the backdrop against which entire planetary systems, and potentially life itself, can quietly develop. The mass of a star at the time it settles onto the main sequence largely determines both its temperature and its overall lifespan, following a relationship astronomers describe using stellar classification. More massive stars burn through their hydrogen fuel considerably faster, despite possessing larger reserves, because their cores operate at higher pressures and temperatures. A star roughly 10 times the mass of the Sun may remain on the main sequence for only about 20 million years, a comparatively brief span. In contrast, a star with only half the mass of the Sun might continue shining steadily for tens of billions of years, far longer than the current age of the universe itself. This wide variation quietly illustrates how mass shapes nearly every aspect of a star's gentle, patient life. Stars are classified according to a spectral sequence often remembered by the phrase "Oh, be a fine girl, kiss me," representing the letters O, B, A, F, G, K, and M in order of decreasing surface temperature. O-type stars are the hottest and most massive, with surface temperatures exceeding 30,000 degrees Celsius and a soft blue-white glow. M-type stars, in contrast, are considerably cooler, with surface temperatures around 3,000 degrees Celsius and a gentle reddish hue. Our Sun is classified as a G-type star, with a surface temperature of approximately 5,500 degrees Celsius and a warm yellow-white glow. This classification system, developed gradually over the early 20th century, remains a quiet cornerstone of modern astronomical study. Within the core of a main sequence star like our Sun, hydrogen fusion proceeds primarily through what is known as the proton-proton chain, a gentle sequence of nuclear reactions that gradually converts hydrogen into helium. This process releases energy in the form of gamma rays, which then take an extraordinarily long journey outward through the dense layers of the star, sometimes requiring tens of thousands of years to reach the surface. Along this slow journey, the energy is repeatedly absorbed and re-emitted, gradually transforming into the visible light that eventually reaches Earth. Once the light finally escapes the star's surface, it takes only about 8 minutes to travel the remaining distance to our planet. This quiet contrast between an internal journey lasting millennia and a final external journey lasting mere minutes offers a gentle reminder of the patient scale on which stars operate. More massive main sequence stars, generally those exceeding about 1.3 times the mass of the Sun, rely primarily on a different fusion pathway known as the carbon-nitrogen-oxygen cycle, or CNO cycle, which uses carbon as a gentle catalyst in converting hydrogen into helium. This process is considerably more sensitive to temperature than the proton-proton chain, allowing these hotter, more massive stars to generate energy at a faster and more efficient rate. The CNO cycle was first described theoretically in 1938 by physicists Hans Bethe and Carl Friedrich von Weizsäcker, working independently around the same time. Though it accounts for only a small fraction of the Sun's own energy output, it dominates energy production in stars somewhat larger and hotter than our own. This quiet distinction in fusion pathways helps explain the wide diversity observed among main sequence stars. The luminosity of a main sequence star, meaning the total amount of energy it radiates each second, varies enormously depending on its mass, following what astronomers call the mass-luminosity relationship. A star with twice the mass of the Sun may be roughly 11 times more luminous, while a star with only half the Sun's mass may be only about 1/20th as luminous. This relationship arises because more massive stars must generate significantly more internal pressure to support their greater weight, resulting in correspondingly higher core temperatures and faster fusion rates. Despite these differences in brightness, the underlying physics governing each star remains gently consistent, following the same quiet principles across the entire range of stellar masses. This relationship allows astronomers to estimate a star's mass simply by measuring how brightly it shines. Our Sun, as a fairly typical main sequence star, converts approximately 600 million tons of hydrogen into helium every second within its core, a quiet and continuous process that has proceeded steadily for over 4 billion years. Despite this immense scale, the Sun loses only a very small fraction of its total mass over its entire main sequence lifetime, owing to the enormous quantity of hydrogen it originally contained. The energy released through this process eventually radiates outward as sunlight, gently warming the Earth and sustaining the conditions necessary for the slow development of life. This steady output has remained remarkably stable throughout recorded human history, varying by only a small fraction of a percent across an 11-year solar cycle. This gentle consistency is part of what has allowed complex life the calm, stable conditions needed to develop gradually over time. Stars on the main sequence maintain their stability through a delicate process known as hydrostatic equilibrium, in which the outward pressure generated by nuclear fusion precisely balances the inward pull of the star's own gravity. Should this balance shift even slightly, the star responds gently and gradually, expanding or contracting slightly until equilibrium is restored once again. This self-regulating quality allows main sequence stars to remain remarkably steady over enormous spans of time, adjusting quietly to small internal changes without dramatic upheaval. This same gentle regulatory process will eventually change as a star exhausts its core hydrogen, setting the stage for the slow transformations of later stellar life. For now, though, this steady balance defines the calm, patient character of a star's longest chapter. Binary and multiple star systems, in which two or more stars orbit a shared center of mass, are remarkably common throughout the galaxy, with some estimates suggesting that more than half of all Sun-like stars exist within such systems. These companion stars can gently influence one another's evolution over time, particularly if they are close enough for material to slowly transfer between them. Alpha Centauri, the closest star system to our own, consists of 3 stars gently bound together by gravity, including a small red dwarf named Proxima Centauri. Studying these systems allows astronomers to measure stellar masses with particular precision, since the orbital motion of companion stars reveals gravitational relationships directly. This quiet companionship among stars adds another gentle layer of complexity to the broader story of stellar life. Toward the later portion of its main sequence life, a star gradually begins to exhaust the hydrogen fuel available within its core, a slow process that unfolds over a considerable span of time rather than occurring suddenly. As core hydrogen becomes more scarce, the fusion rate begins to shift gently, and the star's internal structure starts to slowly reorganize in preparation for its next evolutionary stage. This transition marks the quiet end of the main sequence phase and the beginning of a new chapter defined by gradual, outward change. The exact timing of this shift depends closely on the star's original mass, with more massive stars reaching this point considerably sooner than smaller ones. This slow transition sets the stage for the next chapter of our journey, in which stars begin their gentle expansion into red giants. A typical main sequence star is organized into several gentle, distinct layers, beginning with the core at its center, where nuclear fusion quietly takes place under conditions of extreme pressure and temperature. Surrounding the core lies the radiative zone, a thick region where energy slowly makes its way outward through repeated absorption and re-emission of photons, a process that can take many thousands of years to complete. Beyond this lies the convective zone in stars like our Sun, where hot material rises gently toward the surface while cooler material sinks slowly back down, forming large, slow-moving currents. At the outer edge sits the photosphere, the visible surface layer from which light finally escapes into space. This layered structure, though invisible to direct observation, has been carefully mapped through decades of patient solar and stellar research. The photosphere, the visible outer layer of a star, is where light produced deep within the core finally escapes into the surrounding darkness of space after its long, slow internal journey. This layer is relatively thin compared to the star's overall size, yet it defines the temperature and color that we observe from great distances. Gentle, granulated patterns are often visible across the photosphere, caused by the slow rising and sinking motion of convective currents just beneath the surface. On our own Sun, these granules typically span about 1,000 kilometers and last for only about 20 minutes before gently reforming elsewhere. This constant, quiet churning gives the surface of the Sun a subtly textured, ever-shifting appearance when observed closely. Above the photosphere lies the chromosphere, a thin, comparatively cooler layer that becomes faintly visible during total solar eclipses as a delicate reddish glow surrounding the darkened disk of the star. Beyond this lies the corona, the star's outermost atmosphere, which extends millions of kilometers into space and reaches temperatures far higher than the surface below it, a phenomenon scientists continue to study carefully. The corona is normally too faint to see against the brightness of the star itself, becoming visible to observers only during the brief, gentle darkness of a total eclipse. Solar wind, a steady stream of charged particles, flows outward continuously from the corona, drifting gently through the solar system. This outer atmosphere, though delicate in appearance, plays an important role in shaping the space environment surrounding a star. Sunspots, temporary regions of reduced temperature on a star's surface, appear as gentle darker patches caused by concentrated magnetic activity that slows the normal flow of convective heat. These regions can persist for days to several weeks before gradually fading, following an irregular cycle that, for our own Sun, spans approximately 11 years from one peak of activity to the next. Though sunspots appear dark in contrast to their surroundings, they are still extremely hot, simply cooler relative to the rest of the surface nearby. Historical observations of sunspots date back many centuries, with some of the earliest recorded sightings noted by astronomers in ancient China. Studying these gentle fluctuations helps scientists understand the broader magnetic behavior occurring quietly beneath a star's surface. A star's magnetic field, generated by the movement of electrically charged plasma within its convective layers, plays a quiet but significant role in shaping much of its observable activity. This process, known as the dynamo effect, arises from the combination of convection and the star's own rotation, gradually twisting and organizing magnetic field lines over time. Stronger magnetic activity is often associated with more frequent solar flares and coronal mass ejections, gentle yet energetic releases of particles and radiation from the star's outer atmosphere. Younger stars, which tend to rotate more rapidly, often display stronger magnetic activity than older, more slowly rotating stars like our Sun. Over billions of years, a star's rotation gradually slows, and its magnetic activity settles into a calmer, more steady pattern. The composition of a typical main sequence star is dominated by hydrogen, which generally makes up around 70 to 75% of its total mass, with helium comprising most of the remainder. Heavier elements, referred to collectively by astronomers as metals regardless of their true chemical nature, typically account for only a small fraction of a star's total composition, often less than 2%. This proportion of heavier elements, known as a star's metallicity, offers quiet clues about the environment in which the star originally formed. Stars formed earlier in the universe's history generally contain fewer heavy elements, since these elements are gradually produced and distributed by earlier generations of stars. Our Sun, having formed relatively later in cosmic history, contains a somewhat higher proportion of heavier elements than many older stars. Stellar rotation varies considerably among different stars, with our Sun completing one full rotation approximately every 25 days at its equator, though this rate slows gently toward its poles. This phenomenon, known as differential rotation, occurs because a star is not a rigid solid body but rather a fluid sphere of plasma, allowing different latitudes to rotate at slightly different speeds. Younger, more massive stars often rotate considerably faster, sometimes completing a full rotation within just a matter of hours or days. Over time, magnetic braking, a gentle process involving the star's magnetic field and stellar wind, gradually slows this rotation as the star ages. This slow deceleration offers astronomers a useful, quiet method for estimating the approximate age of a star. Stellar oscillations, subtle and rhythmic pulsations in a star's brightness and size, offer astronomers a quiet window into the star's internal structure through a field known as asteroseismology. These gentle oscillations arise from sound waves traveling slowly through the star's interior, causing tiny, rhythmic changes in surface brightness that can be measured with sensitive instruments. The Kepler Space Telescope, launched in 2009, gathered extensive data on these subtle stellar vibrations across thousands of stars during its mission. By studying the pattern of these oscillations, scientists can gently estimate a star's age, size, and internal composition without needing to observe it directly. This delicate technique has quietly expanded our understanding of stars far beyond what surface observations alone could reveal. The overall size of a main sequence star varies considerably depending on its mass, with the smallest red dwarfs measuring only about 1/10 the diameter of the Sun, while the largest main sequence stars can span many times the Sun's width. Despite these size differences, main sequence stars remain remarkably stable in their proportions throughout most of this stage of life, changing only very gradually over long stretches of time. Red dwarfs, the most common type of star in the galaxy, burn their hydrogen fuel extremely slowly and gently, allowing them to remain on the main sequence for extraordinarily long periods, sometimes exceeding 1 trillion years. Because the universe is currently less than 14 billion years old, no red dwarf has yet had sufficient time to exhaust its fuel. This quiet fact means that every red dwarf ever formed still continues to shine gently today. Astronomers estimate that there are several 100 billion stars within the Milky Way galaxy alone, each one following its own quiet, patient path through the stages of stellar life described throughout this documentary. The vast majority of these stars, roughly 75%, are red dwarfs, small and dim compared to our own Sun yet remarkably long-lived. Larger, brighter stars such as blue giants are considerably rarer, representing only a small fraction of the galaxy's total stellar population. This quiet diversity, spanning enormous differences in size, temperature, and lifespan, reflects the many different paths a collapsing cloud of gas and dust can gently take. As we move forward through this documentary, we will follow stars of varying mass along their differing evolutionary journeys, from stable adulthood toward their eventual, gentle transformations. When a star like our Sun gradually exhausts the hydrogen fuel available within its core, it begins a slow and graceful transformation into what astronomers call a red giant. With core fusion no longer generating sufficient outward pressure, gravity slowly compresses the core further, causing it to heat, while hydrogen fusion continues gently in a thin shell surrounding it. This shell burning releases considerable energy, causing the star's outer layers to expand gradually outward over hundreds of thousands of years. As these outer layers expand, they cool, shifting the star's surface color slowly from yellow toward a deeper, softer orange and red. Our own Sun is expected to enter this red giant phase in roughly 5 billion years, gradually swelling outward toward the orbit of Mercury and Venus. As a red giant continues to expand, its outer layers become increasingly diffuse and cool, sometimes reaching a diameter over 100 times that of the Sun's original size during the main sequence phase. Despite this dramatic increase in size, the overall density of these outer layers becomes extremely low, thinner in places than the air found in Earth's own atmosphere. Meanwhile, the core continues to contract gently under gravity, growing hotter and denser as it awaits the conditions necessary for the next stage of fusion. This contrast between an enormous, gently glowing outer envelope and an increasingly compact, hot core defines much of the character of this stage. Betelgeuse, a well-known red giant located in the constellation Orion, offers observers a visible example of this expanded, softly glowing stage of stellar life. Once the core of a red giant reaches a temperature of approximately 100 million degrees Celsius, helium fusion begins, a process that converts helium into carbon and oxygen through a reaction known as the triple alpha process. In stars with roughly the mass of our Sun, this ignition occurs relatively suddenly in a phenomenon called the helium flash, though the resulting change in the star's outer appearance unfolds gradually and gently over time. This new fusion process provides a fresh, temporary source of internal energy, causing the star to settle into a somewhat more stable, though still evolving, configuration. During this phase, the star may actually shrink slightly and increase in surface temperature, moving to a stage sometimes called the horizontal branch. This gentle adjustment represents another quiet chapter in the star's long, gradual transformation. As helium fusion in the core eventually comes to an end, a Sun-like star enters what is known as the asymptotic giant branch phase, during which it expands once again, this time even further than during its earlier red giant stage. During this period, the star experiences gentle, repeated pulsations, alternately fusing helium and hydrogen in thin shells surrounding an increasingly compact carbon-oxygen core. These pulsations can cause the star to gradually shed some of its outer material into space in slow, gentle waves, forming an expanding envelope of gas and dust around it. This shedding process becomes increasingly important as the star nears the end of this stage, setting the foundation for the formation of a planetary nebula. Mira, a well-studied variable star in the constellation Cetus, offers astronomers a visible example of this pulsating, gently shedding stage of stellar evolution. Over the course of thousands of years, a star in its final giant phase gradually and gently releases the majority of its outer layers into the surrounding space, a slow process driven by pulsations and stellar winds rather than any sudden event. This expelled material drifts gradually outward, eventually forming the soft, glowing structure known as a planetary nebula, illuminated from within by the star's remaining hot core. What remains behind at the center is a small, extremely dense object known as a white dwarf, composed primarily of carbon and oxygen. This remaining core, though no longer capable of sustaining fusion, continues to glow gently from residual heat for billions of years. This quiet, patient shedding process represents one of the primary ways that heavier elements are gradually returned to the interstellar medium. White dwarfs are remarkably dense objects, typically containing a mass comparable to our Sun compressed into a volume roughly the size of Earth, resulting in an average density of about 1 ton per cubic centimeter. This extreme density is supported not by nuclear fusion, which has ceased entirely, but by a quantum mechanical phenomenon known as electron degeneracy pressure, which gently resists further gravitational collapse. Without any internal energy source, a white dwarf slowly and gradually cools over an immense span of time, its light dimming gently across billions of years. The Chandrasekhar limit, named after astrophysicist Subrahmanyam Chandrasekhar who calculated it in 1930, defines the maximum mass a white dwarf can possess while remaining supported by electron degeneracy pressure, approximately 1.4 times the mass of the Sun. Should a white dwarf gradually accumulate additional mass beyond this threshold, perhaps by slowly drawing material from a nearby companion star, its internal balance can no longer be maintained. Chandrasekhar developed this calculation as a young researcher, and his work was initially met with quiet skepticism before later becoming a foundational principle in stellar astrophysics. This limit plays an important role in understanding certain types of stellar transformations that occur within binary star systems. The gentle, steady accumulation of material in such systems can unfold gradually over millions of years before reaching this critical threshold. Not all stars follow the same evolutionary path toward becoming a white dwarf, as this outcome is generally reserved for stars with an initial mass below approximately 8 times that of our Sun. Stars exceeding this threshold follow a considerably different and more layered path, developing internal structures capable of fusing progressively heavier elements within their cores over successive stages. This distinction in mass represents one of the most important dividing lines in stellar evolution, determining whether a star will end its life as a gently cooling white dwarf or undergo the more elaborate transformation we will explore in later chapters. The exact threshold can vary somewhat depending on a star's composition and rotation, but the general principle remains a useful guide. This quiet fork in stellar destiny, determined almost entirely by a star's original mass, shapes the entire remaining story of its evolution. Globular clusters, dense spherical collections of very old stars, offer astronomers a particularly valuable setting for studying the aging process across large numbers of stars formed at approximately the same time. These clusters, some containing hundreds of thousands of stars gently bound together by gravity, can be found orbiting the outer regions of galaxies like our own Milky Way. Because all stars within a given cluster formed within a relatively narrow window of time, differences in their current evolutionary stage largely reflect differences in their original mass. Omega Centauri, the largest known globular cluster associated with the Milky Way, contains an estimated 10 million stars spanning a wide range of evolutionary stages. Observing such clusters allows scientists to gently piece together a detailed timeline of stellar aging across an enormous population of stars. The gradual transformation of stars from stable adulthood into red giants and eventually into white dwarfs or other remnants represents one of the primary mechanisms by which chemical elements are returned to the broader galaxy. Material gently expelled during the giant phase, enriched with elements such as carbon, nitrogen, and oxygen produced through fusion, slowly mixes back into the surrounding interstellar medium. This recycled material can later become part of new molecular clouds, eventually contributing to the formation of future generations of stars and planets. In this quiet, patient way, the elements that make up much of the world around us, and indeed much of our own bodies, trace their origin back to the slow, graceful aging of stars that lived and gently transformed long before our solar system existed. This ongoing cycle of formation, aging, and gentle renewal forms a central theme throughout the remainder of this documentary. The gradual transformation of stars from stable adulthood into red giants and eventually into white dwarfs or other remnants represents one of the primary mechanisms by which chemical elements are returned to the broader galaxy. Why material gently expelled during the giant phase, enriched with elements such as carbon, nitrogen, and oxygen produced through fusion, slowly mixes back into the surrounding interstellar milieu. This recycled material can later become part of new molecular clouds, eventually contributing to the formation of future generations of stars and planets. In this quiet, patient way, the elements that make up much of the world around us, and indeed much of our own bodies, trace their origin back to the slow, graceful aging of stars that lived and gently transformed long before our solar system existed. This ongoing cycle of formation, aging, and gentle renewal forms a central theme throughout the remainder of this documentary. Why? Massive stars, generally defined as those with an initial mass exceeding roughly 8 times that of our Sun, follow a considerably more layered and complex evolutionary path than their smaller counterparts. These stars burn through their hydrogen fuel at a much faster rate, owing to their higher core temperatures and pressures, resulting in comparatively brief lifespans measured in millions rather than billions of years. Once core hydrogen is exhausted, these stars begin fusing progressively heavier elements in succession, developing a layered internal structure often compared gently to the layers of an onion. Each new fusion stage proceeds more quickly than the last, with heavier elements burning through their available fuel in increasingly shorter spans of time. This accelerating internal rhythm marks a key distinguishing feature between massive stars and the more gently paced evolution of Sun-like stars. Following hydrogen and helium fusion, a massive star's core gradually begins fusing carbon into heavier elements such as neon, oxygen, and magnesium, a process that typically unfolds over several hundred years, remarkably brief compared to earlier fusion stages. This carbon-burning phase generates temperatures around 600 million degrees Celsius, considerably hotter than the conditions found in smaller, Sun-like stars. As each successive fusion stage proceeds, the timescales continue to shorten dramatically, reflecting the star's rapidly rising internal temperature and pressure. Oxygen burning, the stage that follows, may last only about 6 months, while silicon burning, the final stage before the core's ultimate transformation, can conclude within a single day. This dramatic acceleration illustrates the increasingly urgent, though still physically gradual and orderly, internal changes occurring within a massive star nearing the end of its fusion-powered life. Silicon burning, the final fusion stage within a massive star's core, gradually produces iron, an element that occupies a particularly important and quiet position within the periodic table due to its exceptionally stable nuclear structure. Unlike the elements fused before it, iron cannot release additional energy through further fusion, since combining iron nuclei actually requires energy input rather than releasing it. As iron gradually accumulates at the center of the star, the core loses its ability to generate outward pressure through fusion, setting the stage for a significant internal transition. This iron core typically grows to a size comparable to Earth, yet contains a mass similar to that of our Sun, compressed into an extraordinarily dense state. This quiet accumulation of iron marks a pivotal, though still calm and gradual, turning point in the life of a massive star. Throughout their brief but active lives, massive stars release considerably stronger stellar winds than smaller stars, gradually shedding significant amounts of mass into the surrounding interstellar medium over the course of their evolution. These winds, composed of charged particles streaming outward from the star's surface, can carry away a substantial fraction of the star's original mass over just a few million years. Wolf-Rayet stars, a particularly active class of massive, evolved stars, are known for exceptionally strong winds that gently strip away their outer hydrogen layers, revealing the helium-rich material beneath. This gradual mass loss can significantly influence the star's later evolution, sometimes altering the mass threshold required for its eventual transformation. The surrounding nebula formed by this shed material often glows softly, illuminated by the intense radiation of the central star. The internal structure of a massive star nearing the end of its fusion stages can be visualized as a series of concentric shells, each one fusing a different element, led gently around an increasingly dense and inactive iron core. Hydrogen continues to fuse gently in the outermost active shell, while helium, carbon, oxygen, neon, and silicon each occupy their own quiet layer closer to the center. This layered structure, sometimes compared to the rings of an onion, reflects the successive stages of fusion the star has gradually passed through over its lifetime. Each layer maintains its own delicate balance of temperature and pressure, contributing to the overall stability of the star even as its core approaches a significant turning point. This intricate internal architecture represents one of the more remarkable and carefully studied aspects of massive stellar evolution. Betelgeuse, one of the most well-known massive stars visible from Earth, resides in the constellation Orion and is currently in a late stage of its evolutionary journey, having expanded into a red supergiant. Located approximately 640 light-years away, this star possesses a radius so large that, if placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter. Despite its immense size, Betelgeuse's outer layers remain quite diffuse, and its surface temperature is considerably cooler than that of our Sun, giving it a distinctive reddish-orange glow visible even without a telescope. Astronomers continue to study this star carefully, observing gentle fluctuations in its brightness that offer clues about the internal processes occurring deep within. Stars like Betelgeuse serve as valuable, nearby Examples of the later stages of massive stellar evolution described throughout this chapter. Supergiant stars, the largest category of stars by physical size, can be classified as either red or blue depending on their surface temperature, with red supergiants being considerably cooler and blue supergiants notably hotter. VY Canis Majoris, one of the largest known stars by radius, is estimated to be over 1,400 times the diameter of our Sun, though its overall mass remains considerably less extreme relative to its size. These enormous stars burn through their nuclear fuel very quickly compared to smaller stars, typically completing their entire evolutionary journey within just a few million years. Despite their brief lifespans on a cosmic timescale, supergiants play an important and gentle role in enriching their surrounding environment with heavier elements produced through their layered fusion processes. Their eventual transformation, which we will explore in the coming chapters, represents one of the more significant events in the ongoing story of stellar and galactic evolution. The core of a massive star, once it becomes composed primarily of iron, can no longer generate energy through fusion and instead relies temporarily on electron degeneracy pressure, the same quantum mechanical support found within white dwarfs, to resist gravitational collapse. However, unlike the stable, long-lasting balance found in white dwarfs, this support proves only temporary in the much more massive and dense iron core of a massive star. As the iron core continues to grow through ongoing silicon burning in the surrounding shell, it gradually approaches a critical mass threshold, similar in principle to the Chandrasekhar limit discussed earlier. This slow, quiet accumulation sets the stage for a significant transformation, one that will be explored in careful detail in the following chapter on supernovae. Even at this late stage, the process remains governed by patient, well-understood physical principles rather than sudden unpredictability. Massive stars, despite their relatively brief lifespans, play a particularly important role in the chemical enrichment of galaxies, as the various elements produced through their successive fusion stages are eventually returned to the surrounding interstellar medium. Elements such as oxygen, neon, magnesium, and silicon, all produced gradually within the layered core of a massive star, contribute significantly to the raw material available for future generations of stars and planets. This gentle, ongoing process of stellar recycling has continued steadily across billions of years of cosmic history, gradually increasing the proportion of heavier elements found throughout the universe. Without the quiet contributions of massive stars, many of the elements essential to rocky planets and biological life, as currently understood, would remain considerably less abundant. This patient, cyclical relationship between massive stars and the broader galaxy underscores their importance despite their comparatively short individual lifespans. As we move toward the next chapter of this documentary, it is worth pausing to gently reflect on the remarkable journey a massive star undertakes, from its early formation within a nebula, through a relatively brief but active main sequence phase, and finally into the layered, rapidly evolving structure described throughout this chapter. Each stage unfolds according to well-understood physical principles, governed by the star's mass and the balance between gravity and internal pressure. The transformation that awaits a massive star at the end of this journey, which we will explore carefully and gently in the chapter ahead, represents one of the most significant and well-studied processes in modern astrophysics. Rather than viewing this transformation as an ending, astronomers often describe it as a continuation, a quiet passing of stellar material back into the wider cosmos. With this gentle framing in mind, let us move softly into the next chapter, where we explore the structure and science of this remarkable stellar transformation. A supernova represents one of the most significant transformations in the life of a massive star, occurring when its iron core can no longer support itself against the pull of gravity and begins to collapse inward within a fraction of a second. This collapse, though sudden at the very center, is the culmination of a slow and patient process that unfolded gradually over millions of years of prior stellar evolution. As the core compresses to an extraordinarily dense state, the outer layers of the star, no longer supported from below, rebound outward in a process astronomers describe using careful mathematical modeling. The resulting release of energy briefly outshines an entire galaxy, allowing supernovae to be observed across enormous cosmic distances. This remarkable event, though often described dramatically in popular culture, is understood by astronomers as a natural and well-documented stage in the ongoing cycle of stellar transformation. Astronomers classify supernovae into two broad categories, Type 1 and Type 2, based primarily on the characteristics observed in their light spectra during the event. Type 2 supernovae occur in massive stars that still retain their outer hydrogen layers at the time of core collapse, producing a spectrum that clearly shows hydrogen's distinctive signature. Type Ia supernovae, in contrast, occur within binary star systems involving a white dwarf that gradually accumulates material from a companion star until it approaches the Chandrasekhar limit described in an earlier chapter. This particular type of supernova produces remarkably consistent peak brightness, allowing astronomers to use them as reliable distance markers, sometimes referred to gently as standard candles. This classification system, refined gradually over decades of careful observation, continues to help astronomers understand the wide variety of ways stars can undergo this significant transformation. During the core collapse of a massive star, an enormous number of neutrinos, nearly massless particles that interact very weakly with other matter, are released within the first few seconds of the event. In fact, the vast majority of the total energy released during this transformation, roughly 99%, is carried away quietly by these neutrinos rather than by visible light. In 1987, astronomers detected a burst of neutrinos from a supernova in the Large Magellanic Cloud, a nearby dwarf galaxy, providing valuable confirmation of theoretical models developed over previous decades. This event, known as SN 1987A, remains one of the most carefully studied stellar transformations in modern astronomical history. The gentle, nearly invisible passage of these neutrinos through detectors on Earth offered scientists a rare and valuable glimpse into the otherwise hidden inner workings of this process. The material released during a supernova travels outward at extraordinary speeds, sometimes exceeding several thousand kilometers per second, gradually slowing as it interacts with surrounding interstellar gas over subsequent centuries. This expanding shell of material forms what astronomers call a supernova remnant, a structure that can remain visible and observable for tens of thousands of years after the initial event. The Crab Nebula, discussed earlier in this documentary, represents one of the most well-studied examples of this expanding remnant, formed from a transformation recorded by astronomers in the year 1054. Over time, this expanding material gradually cools and mixes gently with the surrounding interstellar medium, contributing new elements to the raw material available for future star formation. This slow, patient dispersal represents one of the primary mechanisms through which heavier elements are distributed throughout a galaxy. The intense conditions present during a supernova, including extraordinarily high temperatures and densities, allow for the rapid formation of elements heavier than iron through a process known as rapid neutron capture, or the R process. Elements such as gold, platinum, and uranium, which cannot be produced through the ordinary fusion processes occurring within a star's core during its earlier stages, are believed to form primarily during these brief but significant events. Recent research has also identified neutron star mergers, a separate phenomenon explored later in this documentary, as another important source of these heavy elements. This quiet, patient process means that much of the gold found on Earth, including any small amount that might be nearby right now, likely traces its origin back to events like these occurring long before our solar system formed. This gentle connection between distant cosmic events and everyday materials offers a quiet sense of continuity across the vast scale of cosmic history. Historical records from various cultures around the world document the observation of supernovae visible to the naked eye, offering a quiet connection between ancient astronomers and modern scientific understanding. The supernova of 1054, which created the Crab Nebula, was carefully recorded by Chinese astronomers, who described a new, bright star visible in daylight for approximately 3 weeks. Similarly, in 1572, the Danish astronomer Tycho Brahe carefully documented a new star, now known as Tycho's supernova, which remained visible for over a year and challenged prevailing ideas about the unchanging nature of the heavens. These careful historical observations, made centuries before the development of modern telescopes, continue to provide valuable data for astronomers studying the resulting remnants today. This quiet continuity between ancient observation and modern astrophysics reflects humanity's long-standing, patient curiosity about the changing night sky. The frequency of supernovae within a typical galaxy like our own Milky Way is estimated to be roughly 1 to 3 events per century, though observation from within our own galaxy can be complicated by intervening dust and gas that gently obscure our view. The most recent supernova confirmed to have occurred within the Milky Way itself is Cassiopeia A, believed to have taken place around the year 1680, though it was not widely recorded at the time. Astronomers continue to study its expanding remnant today, located about 11,000 light-years away, using both visible light and X-ray telescopes to gently map its structure. Observations of supernovae in other, more distant galaxies help supplement our understanding, offering additional examples of this transformation process occurring at a safe, comfortable distance. This patient, ongoing observational effort continues to refine scientific understanding of how frequently these transformations occur across different types of galaxies. The light released during a supernova follows a predictable pattern over time, rising quickly to peak brightness before gradually and gently fading over the following weeks and months, a pattern astronomers refer to as a light curve. Type Ia supernovae display particularly consistent and well-understood light curves, a quality that makes them valuable tools for measuring cosmic distances with considerable precision. By carefully comparing the observed brightness of a distant supernova to its known intrinsic brightness, astronomers can calculate its distance using a gentle mathematical relationship. This technique played an important role in the late 1990s discovery that the expansion of the universe is gradually accelerating, a finding that earned researchers the Nobel Prize in Physics in 2011. This quiet, Patient use of distant stellar transformations as measuring tools illustrates the far-reaching value of studying these events carefully. Following a Type II supernova, the collapsed core left behind may become either a neutron star or, in cases involving particularly massive progenitor stars, an even more compact object known as a black hole, both of which will be explored in careful detail in the chapters ahead. The determining factor between these two outcomes relates closely to the mass of the original core, with a threshold generally estimated to be around 2 to 3 times the mass of the Sun. Stars whose cores fall below this threshold typically leave behind a neutron star, while those exceeding it may continue collapsing further into a black hole. This gentle branching point represents one of the more fascinating aspects of massive stellar evolution, connecting the dramatic transformation of a supernova to the quiet, long-lasting remnants that follow. Understanding this relationship required decades of careful theoretical work combined with patient observational study. As we move gently from this chapter on supernovae into the next, focused on the neutron stars that often remain behind, it is worth pausing to appreciate the remarkable scale of transformation involved in this process. A star that once measured many times the diameter of our Sun can, within a matter of seconds, leave behind a core compressed into a sphere only about 20 kilometers across. This quiet contrast between enormous scale and extreme compression reflects the patient, well-understood physics governing gravity, pressure, and nuclear matter under extraordinary conditions. Rather than an ending, astronomers view this transformation as the beginning of another long, stable chapter, one in which the remaining stellar core settles gently into a new, dense form that can persist for billions of years. With this gentle framing in mind, let us move softly into the next chapter, where we explore the quiet, dense world of neutron stars. A neutron star forms from the collapsed core of a massive star, compressed to such an extraordinary degree that protons and electrons are gently forced together to form neutrons, giving the object its descriptive name. Despite containing a mass often between 1.4 and 2 times that of our Sun, a typical neutron star measures only about 20 kilometers in diameter, roughly the size of a modest city. This extreme compression results in a density so remarkable that a single teaspoon of neutron star material would have a mass comparable to a mountain here on Earth. The concept of neutron stars was first proposed theoretically in 1934 by astronomers Walter Bade and Fritz Zwicky, well before any observational evidence confirmed their existence. This quiet, patient theoretical prediction was later confirmed decades afterward, marking one of the more remarkable achievements in the history of astrophysics. The interior structure of a neutron star remains an area of active and careful scientific study, with current models suggesting several distinct layers, each governed by extreme physical conditions unlike anything found elsewhere in the universe. The outer crust is believed to consist of a rigid lattice of atomic nuclei, gradually transitioning into a fluid interior composed primarily of neutrons as depth increases. At the very center, some theoretical models propose the possible presence of exotic states of matter, though this remains an area of gentle scientific inquiry rather than settled consensus. The surface gravity of a neutron star is extraordinarily strong, roughly 200 billion times that experienced on the surface of Earth. This combination of extreme density, pressure, and gravity makes neutron stars valuable natural laboratories for studying physics under conditions that cannot be replicated here on Earth. Many neutron stars rotate at remarkable speeds, a natural consequence of the conservation of angular momentum during the original star's gradual collapse, much as a figure skater gently spins faster when drawing their arms inward. Some neutron stars complete hundreds of rotations every second, an extraordinary rate for an object containing more mass than our Sun. The fastest known neutron star, discovered in 2006 and designated PSR J1748-2446 AD, rotates at a rate of approximately 716 times per second. Despite this rapid rotation, the surface of a neutron star remains remarkably smooth, with any surface irregularities measuring only a few millimeters in height due to the immense gravitational forces at play. This combination of rapid rotation and smooth structure reflects the quiet, orderly physics governing these dense stellar remnants. The magnetic field surrounding a typical neutron star is extraordinarily strong, often trillions of times more powerful than the magnetic field generated by Earth, a property that arises from the compression of the original star's magnetic field during collapse. This intense magnetic field plays a central role in many of the observable phenomena associated with neutron stars, including the emission of focused beams of radiation from their magnetic poles. As a neutron star rotates, these beams sweep gently across space, and if aligned favorably toward Earth, can be detected as a very regular, rhythmic pulse of radiation. This particular class of neutron star, discussed in greater detail in the following chapter, is known as a pulsar. The steady, reliable timing of these pulses has made certain neutron stars valuable tools for testing fundamental physics and even for navigation purposes in deep space. Neutron stars, despite their compact size, often retain a portion of the original star's residual heat, allowing their surfaces to reach temperatures of several 100,000 to over 1,000,000 degrees Celsius shortly after formation. This immense heat radiates outward gradually over thousands to millions of years, causing the neutron star to slowly cool over an extraordinarily long span of time. Astronomers study this cooling process carefully using X-ray telescopes, since neutron stars emit much of their thermal radiation at these shorter wavelengths rather than in visible light. The Cassiopeia A neutron star, associated with the supernova remnant discussed in the previous chapter, has provided valuable data on this gradual cooling process since its discovery in 1999. This patient, long-term cooling represents yet another example of the slow, gentle timescales that govern much of stellar evolution, even in its more compact remnant stages. Binary systems containing a neutron star and a companion star offer astronomers valuable opportunities to study the gentle gravitational relationship between these two very different types of objects. In some cases, material from the companion star can gradually spiral inward toward the neutron star, forming a glowing accretion disk and releasing energy in the form of X-rays as it slowly falls inward. These systems, known as X-ray binaries, provide important insight into the mass and physical properties of neutron stars through careful measurement of their orbital motion. Cygnus X1, though actually associated with a black hole rather than a neutron star, was one of the first X-ray binary systems studied in detail, paving the way for research into similar neutron star systems. This quiet, patient study of binary interactions continues to refine scientific understanding of these dense stellar remnants. The maximum possible mass of a neutron star remains an area of ongoing, careful scientific investigation, with current estimates suggesting an upper limit of approximately 2.2 to 2.3 times the mass of the Sun, a boundary known as the Tolman-Oppenheimer-Volkoff limit. Beyond this threshold, The immense gravitational pull is believed to overcome even the quantum mechanical pressures supporting the neutron star, leading to further collapse into an even more compact object. This limit was first explored theoretically in 1939 by physicists Robert Oppenheimer and George Volkoff, building upon earlier work by Richard Tolman. Precisely determining this boundary requires a detailed understanding of how matter behaves under the most extreme densities found anywhere in the universe, an area where theoretical and observational astrophysics continue to gently inform one another. This patient, ongoing research helps refine the quiet boundary between neutron stars and the even more compact objects explored later in this documentary. Gravitational waves, ripples gently distorting the fabric of space and time itself, were first predicted theoretically by Albert Einstein in 1916 as a consequence of his general theory of relativity. It was not until 2015 that these waves were directly detected for the first time, using the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO, confirming a prediction that had patiently awaited observational evidence for nearly a century. In 2017, LIGO and its European counterpart, Virgo, detected gravitational waves produced by the merger of two neutron stars, an event also observed simultaneously across the electromagnetic spectrum. This combined observation, known as multi-messenger astronomy, provided valuable confirmation that such mergers contribute to the production of heavy elements discussed in the previous chapter. This remarkable achievement, built upon decades of patient theoretical and technological development, opened an entirely new gentle window through which to observe the universe. Neutron stars occasionally experience sudden, small changes in their rotation rate, known as glitches, believed to result from gentle internal adjustments within their dense interior structure. These glitches, though technically abrupt, involve only extremely tiny changes in rotation speed, sometimes altering the pulse rate by less than 1 part in a million. Astronomers believe these events occur when the neutron star's rigid outer crust gently readjusts relative to its more fluid interior, a process still being carefully studied and modeled. The Vela pulsar, one of the most closely monitored neutron stars, has experienced numerous documented glitches since its discovery in 1968, providing valuable data for understanding neutron star interiors. Studying these subtle timing variations offers astronomers a quiet, indirect method for probing the otherwise hidden internal structure of these remarkably dense objects. Over time spans reaching into billions of years, neutron stars continue to exist quietly within galaxies, gradually cooling and, in many cases, gradually slowing their rotation as they radiate away energy through the emission of particles and radiation. Unlike white dwarfs, which cool gently while maintaining a relatively stable size, neutron stars remain remarkably compact throughout this entire process, supported by the same quantum mechanical principles that resisted their initial collapse. It is estimated that our galaxy alone contains hundreds of millions of neutron stars, the vast majority of which remain too faint or too distant to be directly detected with current instruments. Those that can be observed, particularly the rotating pulsars discussed in the next chapter, offer valuable and quietly fascinating windows into the physics of extreme density. As we continue this documentary, we now turn gently toward these rotating neutron stars, whose steady, rhythmic pulses have earned them a distinctive and gentle place within the study of stellar remnants. Pulsars are a particular type of rotating neutron star that emit steady, focused beams of radiation from their magnetic poles, appearing to gently pulse on and off as these beams sweep past Earth with each rotation. This effect is often compared to the gentle, rhythmic sweep of a lighthouse beam, appearing to flash only when its light happens to point directly toward an observer. The first pulsar was discovered in 1967 by astronomer Jocelyn Bell Burnell, then a graduate student, who noticed an unusually regular radio signal while reviewing data from a radio telescope array. This discovery initially puzzled researchers, who briefly and playfully considered the possibility of an artificial origin before quietly settling on the now well-understood explanation involving rotating neutron stars. This remarkable finding opened an entirely new field of study within astrophysics, one that continues to reveal gentle insights into the nature of these dense, rapidly spinning objects. The regularity of a pulsar's emitted signal is remarkably precise, in some cases rivaling the accuracy of atomic clocks here on Earth, a quality that has proven valuable for a wide range of scientific applications. Millisecond pulsars, a particularly fast-spinning subclass, rotate hundreds of times per second and maintain such consistent timing that astronomers have used them to test aspects of Einstein's theory of general relativity with great precision. The Hulse-Taylor binary pulsar, discovered in 1974, provided some of the earliest indirect evidence for the existence of gravitational waves, a finding that earned its discoverers the Nobel Prize in Physics in 1993. This binary system, consisting of two neutron stars gently orbiting one another, has been monitored carefully for decades, with its orbital decay matching theoretical predictions with remarkable precision. This patient, long-term observation stands as one of the quiet triumphs of modern observational astrophysics. Pulsars gradually lose rotational energy over time, causing their spin rate to slow very gently across thousands to millions of years, a process astronomers refer to as spin down. This gradual slowing occurs as the pulsar radiates away energy through its magnetic field and the particles it emits, a quiet and continuous process that can be measured with great precision using radio telescopes. Eventually, after a sufficiently long period, a pulsar's rotation may slow to the point where it can no longer generate a detectable beam of radiation, entering a quiet phase sometimes referred to as a dead pulsar. However, in binary systems, a slowing pulsar can sometimes gently regain rotational speed by drawing material from a companion star, a process that can produce the rapidly spinning millisecond pulsars mentioned earlier. This quiet interplay between gradual slowing and occasional renewal adds a gentle layer of complexity to the long-term evolution of these fascinating objects. Magnetars represent a particularly distinctive class of neutron star, characterized by an exceptionally powerful magnetic field, often 1,000 times stronger than that of a typical neutron star and roughly a quadrillion times stronger than Earth's own magnetic field. These extraordinarily strong fields are believed to arise from unique conditions during the star's collapse, though the precise mechanism remains an area of continued, careful scientific study. Magnetars occasionally release brief, gentle bursts of X-rays and gamma rays, believed to result from subtle adjustments or gentle fractures within their rigid outer crust. The first magnetar was identified in the late 1990s, following decades of theoretical prediction dating back to work in the 1990s by astrophysicists Robert Duncan and Christopher Thompson. Roughly 30 magnetars have been identified within our galaxy to date, representing a small but scientifically valuable subset of the broader neutron star population. The surface of a magnetar is subject to extraordinary magnetic stresses, occasionally leading to gentle rearrangements of its rigid crust, an event sometimes compared, quite loosely, to the settling adjustments observed within Earth's own crust over geological time. These adjustments can release brief bursts of high-energy radiation, detectable by specialized space telescopes designed to observe X-rays and gamma rays. SGR 1806-20, a well-studied magnetar located roughly 50,000 light-years away, released one of the most energetic bursts ever recorded from a magnetar in December 2004, briefly affecting Earth's upper atmosphere in a measurable, though harmless, way. Such events, while notable for their energy output, occur at a safe distance and pose no meaningful concern for observers here on Earth. Studying these bursts carefully continues to refine scientific understanding of the extreme physics governing these unusually magnetic stellar remnants. Radio telescopes remain the primary instrument used to detect and study most known pulsars, capturing the regular, rhythmic radio emissions produced as their beams sweep gently across the sky. The Parkes Observatory in Australia and the Arecibo Observatory in Puerto Rico, though the latter is no longer operational, each played a significant historical role in expanding the catalogue of known pulsars throughout the latter half of the 20th century. More recently, the 500-meter aperture spherical telescope in China, completed in 2016, has continued this work, gently discovering hundreds of additional pulsars through careful, patient observation. Each newly discovered pulsar adds to a growing catalogue that helps astronomers understand the distribution and characteristics of neutron stars throughout our galaxy. This ongoing, methodical survey work represents a quiet but essential aspect of modern observational astrophysics. The discovery of pulsars in the late 1960s provided important indirect confirmation of the theoretical existence of neutron stars, a concept that had been proposed decades earlier but lacked observational evidence until that point. This gentle confirmation helped bridge the gap between theoretical astrophysics and observational astronomy, encouraging further research into other extreme stellar phenomena. The pulsar found at the center of the Crab Nebula, discussed in earlier chapters, rotates approximately 30 times per second and continues to be one of the most closely studied objects of its kind. Its steady, reliable pulse has been monitored continuously since its discovery in 1968, providing a valuable long-term dataset for astronomers studying the gradual spin-down process described earlier in this chapter. This continuity of careful observation across more than 5 decades reflects the patient, long-term nature of much astronomical research. Pulsar timing arrays, a network of carefully monitored millisecond pulsars distributed across the sky, offer astronomers a unique method for detecting extremely gentle, long-wavelength gravitational waves that would otherwise remain undetected by instruments like LIGO. By carefully measuring tiny, patient variations in the arrival times of pulses from multiple pulsars simultaneously, researchers can search for the subtle gravitational influence of events such as the slow, gradual merging of supermassive black holes at the centers of distant galaxies. In 2023, several research collaborations announced evidence consistent with a faint, gentle background hum of gravitational waves detected through this careful, patient method. This achievement, built upon decades of consistent pulsar monitoring, illustrates the quiet, cumulative value of long-term astronomical observation. Continued monitoring of these cosmic lighthouses promises to reveal further gentle insights into the large-scale structure and history of the universe. Not all magnetars exhibit continuous activity, and many spend long stretches of time in a relatively quiet state, punctuated only occasionally by the brief bursts of radiation described earlier in this chapter. Some magnetars, once thought to be entirely separate from ordinary pulsars, have since been observed to occasionally exhibit pulsar-like radio emissions, suggesting a gentle overlap between these two categories of neutron star. This blurring of categories reflects the ongoing, careful refinement of scientific understanding as new observational data becomes available. Researchers continue to study the relationship between magnetars, ordinary pulsars, and other neutron star varieties, gradually building a more complete and nuanced picture of this diverse family of stellar remnants. This patient scientific process, marked by gentle revision and careful reconsideration, reflects the broader, unhurried nature of astronomical discovery. As this chapter draws to a gentle close, it is worth reflecting on the remarkable diversity found within the neutron star family, ranging from the steady, rhythmic pulsars to the intensely magnetic and occasionally active magnetars. Each of these objects, though sharing a common origin in the collapsed core of a massive star, displays its own quiet, distinctive characteristics shaped by factors such as rotation speed, magnetic field strength, and binary companionship. Continued observation using radio, X-ray, and gravitational wave instruments promises to reveal further gentle insights into this fascinating population of stellar remnants in the years ahead. As we move forward into the next chapter, we will explore the even more extreme outcomes that can occur when a stellar core exceeds the mass limits discussed earlier, gently transitioning our focus toward black holes and other compact remnants. This patient exploration continues to expand our quiet understanding of the many forms a star's material can ultimately take. When the collapsed core remaining after a supernova exceeds the maximum mass a neutron star can support, generally estimated at around 2.2 to 2.3 times the mass of the Sun, gravity continues to compress the material further, gradually forming what is known as a stellar mass black hole. Unlike the objects discussed in previous chapters, a black hole is defined not by a solid surface but by a boundary known as the event horizon, beyond which the gentle pull of gravity becomes so strong that not even light can escape. This concept was first explored theoretically through the equations of general relativity, developed by Albert Einstein in 1915, though the term black hole itself was not popularized until physicist John Wheeler used it in 1967. Despite their reputation in popular culture, black holes are understood by astronomers as a natural and well-modeled outcome of stellar evolution, following orderly physical principles. This quiet, mathematical understanding allows scientists to study black holes carefully despite never being able to observe their interior directly. The event horizon of a black hole, the boundary beyond which nothing can gently escape its gravitational pull, has a size directly related to the object's mass, described mathematically by what is known as the Schwarzschild radius. For a black hole with a mass equal to that of our Sun, this radius would measure only about 3 kilometers, an extraordinarily compact scale compared to the star's original size. Stellar mass black holes, formed from the collapse of massive stars, typically range from about 5 to several tens of times the mass of the Sun. Despite their compact size, black holes continue to exert gravitational influence on their surroundings in the same gentle, predictable way as any other massive object, following the same orbital principles that govern planets around stars. This quiet consistency with established physics helps astronomers study black holes indirectly, through their gravitational effect on nearby matter. Because black holes do not emit light themselves, astronomers must rely on gentle, indirect methods to detect and study them, primarily by observing their gravitational influence on nearby stars and gas. In binary systems where a black hole orbits a companion star, material can gradually spiral inward, forming a glowing accretion disk that emits X-rays as it slowly heats through friction and gravitational compression. Cygnus X1, mentioned briefly in an earlier chapter, was one of the first objects strongly suspected to be a black hole, identified through this careful method in the early 1970s. The 2019 image released by the Event Horizon Telescope collaboration, showing the shadow of a supermassive black hole at the center of Galaxy Messier 87, represented a landmark achievement built upon decades of careful, patient technological development. This remarkable image offered humanity its first direct visual glimpse of the gentle boundary surrounding a black hole. Supermassive black holes, a distinctly different category from the stellar mass black holes discussed earlier, are found at the centers of most large galaxies, including our own Milky Way, and can contain masses ranging from hundreds of thousands to billions of times that of our Sun. The supermassive black hole at the center of our galaxy, named Sagittarius A*, has a mass estimated at approximately 4.3 million times that of the Sun and was directly imaged by the Event Horizon Telescope collaboration in 2022. The formation process of these enormous objects remains an area of continued, careful scientific investigation, with several gentle theories proposed involving the gradual merging of smaller black holes or the direct collapse of extremely massive early gas clouds. Despite their enormous mass, supermassive black holes occupy a relatively small region at the very center of their host galaxy, exerting a gentle gravitational influence on the surrounding stars and gas over vast distances. This quiet, central presence plays an important role in shaping the overall structure and evolution of galaxies over cosmic time. Black holes are described by physicists using only a small number of measurable properties, primarily mass, electric charge, and angular momentum, a principle sometimes referred to gently as the no-hair theorem, since no additional distinguishing details are believed to remain observable from the outside. This elegant simplicity, despite the extreme and complex physics involved in a black hole's formation, reflects a quiet mathematical order underlying these otherwise mysterious objects. Rotating black holes, described mathematically through a solution developed by physicist Roy Kerr in 1963, exhibit a slightly different structure than their non-rotating counterparts, gently dragging the surrounding space along with their rotation. This effect, known as frame dragging, has been carefully measured around Earth itself, though to an extraordinarily small degree, through satellite experiments conducted in the early 21st century. This quiet confirmation of relativistic effects, even in far gentler conditions than those found near a black hole, reflects the broad and consistent applicability of Einstein's theoretical framework. Gravitational time dilation, a gentle consequence of Einstein's general theory of relativity, causes time to pass more slowly in regions of stronger gravitational influence, an effect that becomes particularly pronounced near a black hole's event horizon. From the perspective of a distant, safe observer, an object approaching a black hole would appear to move increasingly slowly, gradually seeming to freeze near the boundary rather than crossing it, at least as far as the outside observer could ever detect. This effect, though most dramatic near black holes, has also been carefully measured in much gentler forms here on Earth, including small but measurable differences between clocks placed at different altitudes. The global positioning system relies on careful, precise corrections for these gentle relativistic effects to maintain accurate timing and location data. This quiet, everyday application of relativistic physics offers a gentle reminder of how deeply these cosmic principles are woven into modern technology. Not every massive star's core collapse results in the dramatic light display of a supernova, and some particularly massive stars may undergo a quieter process sometimes referred to as a failed supernova, in which the core collapses directly into a black hole with comparatively little visible light released. Astronomers identified a possible example of this quiet phenomenon in 2017, involving a massive star that simply and gently faded from view over a period of months rather than producing the expected bright transformation. This gentle, quiet outcome offers an alternative pathway toward black hole formation, distinct from the more commonly observed supernova process described in earlier chapters. Continued observation of massive stars nearing the end of their evolutionary journey may help astronomers better understand how frequently this quieter pathway occurs compared to the more dramatic alternative. This ongoing, patient research reflects the still evolving nature of scientific understanding regarding the final stages of massive stellar life. The merging of two black holes, an event first directly detected through gravitational waves in September 2015 by the LIGO collaboration, represents one of the most energetic gentle processes known to occur in the universe, despite producing no visible light whatsoever. This particular merger involved two black holes with masses of approximately 29 and 36 times that of our Sun, combining gently to form a single, larger black hole while releasing an immense burst of gravitational wave energy. The resulting ripples in space-time traveled outward for approximately 1.3 billion years before gently reaching Earth, where they were detected as an extraordinarily small, precisely measured stretching and compressing of space. This landmark detection confirmed a prediction made by Einstein a century earlier and earned three of the project's lead researchers the Nobel Prize in Physics in 2017. Since this first detection, dozens of additional black hole mergers have been carefully identified, gradually building a more complete picture of these quiet, energetic cosmic events. Primordial black holes, a theoretical category distinct from those formed through stellar collapse, are hypothesized to have formed during the earliest moments following the Big Bang, arising from small, dense fluctuations in the very early universe rather than from the death of a star. These hypothetical objects, which could range in mass from far smaller than our Sun to considerably larger, have not yet been conclusively observed, though they remain a gentle area of active theoretical and observational research. Some researchers have proposed that primordial black holes might contribute to the mysterious dark matter that appears to gently influence the rotation of galaxies, though this remains one hypothesis among several under careful consideration. Ongoing surveys continue to search patiently for gentle gravitational evidence of these theoretical objects, using methods similar to those developed for detecting stellar mass black holes. This quiet, open area of research reflects the continually evolving nature of our understanding regarding the full population of black holes that may exist throughout the universe. As this chapter draws to a gentle close, it is worth reflecting on the remarkable range of outcomes that can follow the collapse of a massive star's core, from the dense, rotating neutron stars discussed in previous chapters to the even more extreme black holes explored here. Each of these outcomes follows naturally from the same underlying physical principles, governed primarily by the original mass of the collapsing core and the delicate balance between gravity and various forms of internal pressure. Despite their sometimes dramatic reputation, both neutron stars and black holes are understood by astronomers as natural, well-modeled products of stellar evolution, following orderly and increasingly well-understood physics. As we move into the final chapter of this documentary, we will step back gently to consider the broader context in which these remarkable objects exist, exploring star clusters, galaxies, and the patient, ongoing cycle of cosmic recycling that connects every stage of stellar life discussed throughout this journey. This gentle widening of perspective offers a fitting, calm conclusion to our slow exploration of the stars. Star clusters, gentle gravitationally bound groups of stars that form together from the same parent molecular cloud, come in two broad varieties: open clusters and globular clusters, each with its own distinct quiet character. Open clusters, such as the well-known Pleiades visible in the constellation Taurus, typically contain a few hundred to a few thousand relatively young stars, loosely bound and gradually drifting apart over hundreds of millions of years. Globular clusters, discussed briefly in an earlier chapter, are considerably older and more densely packed, often containing hundreds of thousands of stars bound tightly together for many billions of years. These differing structures offer astronomers valuable, complementary windows into stellar evolution across a wide range of ages and environments. Observing both types of clusters together provides a gentle, patient timeline spanning nearly the entire history of star formation within our galaxy. Galaxies themselves, vast gravitationally bound systems containing anywhere from a few million to several trillion stars, provide the broader gentle context within which the entire stellar life cycle described throughout this documentary unfolds. Our own Milky Way, a barred spiral galaxy, contains an estimated 100 to 400 billion stars arranged gently within a flattened, rotating disk spanning roughly 100,000 light-years in diameter. Within this vast structure, new stars continue to form quietly within nebulae, while older stars gradually age, transform, and eventually return their material to the surrounding interstellar medium. This continuous, patient cycle of formation, evolution, and gentle renewal has repeated countless times since the galaxy's formation, roughly 13.6 billion years ago. Understanding this broader galactic context helps astronomers appreciate how individual stars, however remarkable on their own, form small yet meaningful threads within a much larger, ongoing cosmic story. The rate at which new stars form within a galaxy, known as the star formation rate, varies considerably depending on the availability of molecular gas and other gentle environmental factors within different regions of the galaxy. Our own Milky Way is estimated to form roughly 1 to 2 new stars, on average, each year, a relatively modest and steady rate compared to some more active galaxies observed elsewhere in the universe. Starburst galaxies, in contrast, can form new stars at rates tens or even hundreds of times higher, often triggered by gentle gravitational interactions or mergers with neighboring galaxies. These differing rates of star formation reflect the diverse conditions found throughout the universe, shaped by each galaxy's unique history and environment. This quiet variation across different galaxies adds further richness to the broader, patient story of stellar birth and evolution. The chemical elements produced through the various stages of stellar evolution described throughout this documentary, from the fusion occurring within main sequence stars to the more intense processes accompanying supernovae, gradually accumulate within a galaxy over successive generations of stars. This gentle, patient process, known as chemical enrichment, means that stars forming later in a galaxy's history generally contain a higher proportion of heavier elements than those formed earlier. Our Sun, having formed relatively late within the Milky Way's history, contains a moderate proportion of these heavier elements, sufficient to support the formation of rocky planets and, eventually, the gentle conditions necessary for life as currently understood. This quiet inheritance, passed gradually from one stellar generation to the next, connects our own solar system to the many generations of stars that lived and gently transformed long before it formed. This patient chemical legacy underscores the deep, gentle interconnectedness running throughout the story of stellar evolution. Our own solar system, including the Sun and all its planets, is believed to have formed from a molecular cloud that had already been gently enriched by the remnants of earlier generations of stars, a process explored throughout this documentary. Evidence for this comes from the presence of certain isotopes found within ancient meteorites, remnants of the early solar system that have remained largely unchanged for over 4.5 billion years. These isotopes, including a form of aluminum that decays gradually over time, suggest that a nearby supernova may have gently influenced the formation of our solar system, either by triggering the initial collapse of the parent cloud or by contributing additional enriched material. This quiet, ancient connection between a long-past stellar transformation and the very formation of our own solar system offers a gentle sense of continuity across the vast scale of cosmic time. Such findings continue to be studied carefully through the careful analysis of meteorite samples collected here on Earth. The local group, the gentle gravitationally bound collection of galaxies that includes our own Milky Way, contains over 80 known galaxies of varying sizes, dominated primarily by the Milky Way and the somewhat larger Andromeda galaxy. These two large spiral galaxies are gradually approaching one another, drawn together gently by mutual gravitational attraction, and are expected to undergo a slow, gradual merger in approximately 4.5 billion years. Despite the vast number of stars contained within both galaxies, the enormous distances separating individual stars mean that direct stellar collisions during this merger are expected to be extraordinarily rare. Instead, the two galaxies will gradually and gently reshape one another's structure over hundreds of millions of years, eventually forming a single, larger galaxy. This slow, patient cosmic dance illustrates yet another example of the unhurried timescales that characterize so much of the universe's gentle evolution. Star formation throughout the universe is not expected to continue indefinitely, as the gradual depletion of available molecular gas within galaxies will eventually slow, and eventually halt, the gentle process of new star birth described throughout this documentary. Current estimates suggest that star formation across the universe has already gradually declined from its peak, which occurred roughly 10 billion years ago, a period sometimes referred to gently as cosmic noon. Despite this gradual decline, new stars continue to form quietly within molecular clouds throughout the present-day universe, including within our own Milky Way galaxy. Astronomers estimate that meaningful star formation may continue for trillions of years into the future, gradually tapering as available gas becomes increasingly scarce. This extraordinarily long, patient timescale offers a gentle reminder of just how early in the universe's story we currently find ourselves. The James Webb Space Telescope, launched in December 2021, has considerably expanded astronomers' ability to gently observe distant star-forming regions and early galaxies, using infrared instruments capable of peering through dust that would otherwise obscure visible light observations. Among its many careful discoveries, the telescope has captured remarkably detailed images of nebulae, protostars, and distant galaxies, gently refining our understanding of many of the processes described throughout this documentary. Its observations of the pillars of creation within the Eagle Nebula, revisited with considerably improved clarity compared to earlier Hubble images, revealed intricate new details about the ongoing, gentle process of star formation within that structure. This continued technological progress reflects humanity's patient, ongoing effort to understand the universe with ever greater clarity and precision. Each new generation of instruments gently builds upon the careful work of those that came before, gradually deepening our collective understanding of the stars. The story of stellar evolution described throughout this documentary, from the quiet gathering of gas within a nebula to the dense, stable remnants left behind after a star's later transformations, represents a patient, cyclical process that has repeated countless times across the history of our galaxy and the wider universe. Each stage in this journey, however different in scale or intensity, follows consistent, well-understood physical principles, patiently studied and refined by generations of careful astronomers and physicists. The material that forms new stars is never entirely new, but rather represents a gentle continuation of material that has been recycled again and again through the lives of countless earlier stars. This quiet, ongoing cycle connects every star visible in the night sky to a long, patient lineage stretching back to the earliest generations of stars formed after the Big Bang. Understanding this cycle offers a gentle, grounding perspective on our own place within the vast, slow unfolding of cosmic time. As this documentary gently draws to its close, it is worth remembering that the calcium in your bones, the iron carried quietly within your blood, and the oxygen you have been breathing throughout this journey were each formed, patiently and gradually, within stars very much like the ones described tonight. You are, in a very real and gentle sense, a small continuation of this same ancient, unhurried cosmic story, formed from material that has traveled an extraordinarily long and patient path to arrive here. There is no need to hold on to every detail described throughout this documentary, only to carry with you a gentle sense of the slow, steady rhythm that connects the stars above to the quiet room around you now. As you drift towards sleep, know that the universe continues its patient, gentle work above you, unhurried and steady, just as it has for billions of years. Rest now, gently, beneath the same quiet stars that have shone, steadily and patiently, since long before you arrived. Thank you for spending these quiet hours with Sleeping with Facts, drifting gently alongside the stars from their first misty beginnings to the dense, patient remnants they leave behind. If your eyes grew heavy somewhere along the way, that was always the gentle hope behind every word. Rest well tonight, knowing the same slow, steady universe will be here again tomorrow, and we will be here too, whenever you are ready to return. Sleep softly, and good night.